This kid. There's a non-zero chance that he is atypical.
You have a desktop and a laptop?
Oh, so for me, I have a desktop. I don't anymore because I think I'm really good. But now I just went for a laptop that performs as well as a desktop.
There you go.
Yeah, I found it annoying having a desktop and a laptop.
Yeah, totally. Yeah. I would never want to do that.
When I was taking your class, like I had a really powerful desktop, so I was like, oh, I'll just get a crappy laptop for coding, and then it turns out like it was way too slow, and so that's when I got this, and then I gave away my desktop because like it was annoying on that laptop. Like I want to have all my stuff in one place, and my desktop is fast, so I would like remote desktop into it. And then just,
It's so funny. I tried to mimic a desktop by using all the USB ports. Essentially. Like, I use the HDMI, I use the keyboard, and it emulates a desktop. They just have a 23-inch screen. This is like a tower with screens.
Yeah, a lot of people do that now. Even my uncle, who's like not into tech, he's like 60-something, he's a business person. He has like 3 monitors, and he just picks up his laptop.
Yeah, that's what I do, yeah. I just have one large monitor.
Yeah.
I tried the 3 monitors, it didn't work for me.
Really?
Yeah. But I know people like it.
Still using Emacs too, right?
Yeah, exactly. All right. Good afternoon, everyone. Any questions? Any questions at all?
If we didn't
Yes.
use math on the third problem in the homework, is that good or bad?
I mean, I don't care. You can obviously do it without map. I thought it saved me a couple lines of code.
Okay.
But if you're satisfied with your answer without map,
So
go for it.
As long as it works and it's within the parameters.
Yes, totally, yeah. And I will give out the solutions tomorrow, and then you can see whether you like mine better or yours better.
Okay. I'd love to see how you did it with math.
Yeah, I want to see.
Yeah, that's the idea. And I figure if I give them out tomorrow morning, that's when everyone's still interested. So as soon as I get up, I'll just post them somehow.
It looks pretty clean with math in my opinion.
Yeah, that's what.
I tried it without, and
Yeah.
then tried it with. I like it.
Yeah. So give it a try. I mean, as long as you're done with the basics. All right. So today we're going to be going into functions as parameters. So here I'm having a function triple. It's a function that maps x to 3 times x. And I'm passing it to this map method here. And you can see it's a parameter I'm passing it in. That's what you can do when you have functions as first class values. So let's implement map. What does map do? Is it takes this function and it applies it to all of the elements on the list. So here is the specification. Map takes a list of integers. I'm just using integers here right now for simplicity. Of course, the map that you find in the Scala library will work for lists of arbitrary types, but to keep the implementation simple and stay away from generics, we'll just keep it simple. So fun is a function that maps an integer to an integer. And what I get is, of course, a list of integers. I'm going to have to write it recursively, and so I have to give the return type. And now this is one of those recursive functions that kind of writes itself. You simply ask yourself, well, what if the list is empty? If the list is empty, then the output is the empty list because there's nothing to do. What if the list is not empty? Well, then I have to compute what is the function when evaluated on the head of the list. And I recursively compute what happens when I map the function to the tail of the list. And then all I have to do is stick those two together with cons. So here, I'm now recursively applying fun to everything. So I'm having a sample call here. There's nothing to it. And then I'll get out 3, 6, 9. Now, again, why are we doing this? The motivation for using functions as parameters is that if you look at this implementation, you see there is a certain amount of stuff that's going on, such as if the list is empty, there's nothing. Otherwise, combine the function applying the head with the tail. That's completely independent of what that function is. if you wanted to compute the sum, then you would add the head and the tail. If you wanted to compute the product, you multiply the head and the tail. If you want to compute the maps, you take the larger of the head and the tail. I shouldn't say that. So that's full. So forget that I said that. With the product, because we're not combining them, we're just applying a function at every point. So if I want to multiply by 3, versus I want to take the square, or whatever it is that I want to do on the head, the basic construction is always the same, but the detail of what I do here differs. So it enables me to kind of write a skeleton and inject in it a specific computation. And that's kind of nice. In Java, we don't normally do these things because it's a little harder to do. I guess nowadays you can use lambda expressions, but think of Java before lambda expressions, and what's really hard to put in a bit of functionality into somewhere, and we didn't do it. All right, so that's the easy part. Now there's a complexity that's also very useful. So let me explain this with an abstract nonsense example here. So I'm having a val n equals 3. I'm having a fun that takes an x and returns n times x. So what is fun of 2? 6, obviously, right? What else could it be? N is 3, x is 2, so it's 6. And this doesn't seem like a big deal. You know, after all, this thing is a val. It's 3. It's always 3. It can never change. So obviously, the function here must multiply by 3. So let's do something a little different. Here I have a function that I call mul_by. It takes an n, that's an int, and it returns a function. It returns the function that takes an x and multiplies it with n. So that looks confusing. So what's mul_by really do? One way to find out what it does is we'll just call it. I'll call mul_by4. Mul_by4 is what? No,
it's a function.
It's a function. Because mul_by of 4 is the function that maps x to 4 times x. That's the point I'm trying to make. Yes?
Isn't this similar to just having a function with 2 parameters?
It is similar and not the same. And hold that thought until Wednesday.
It's like a functional pattern, right?
Yes. So that's exactly what we're talking on Wednesday. But right now, we're just going to follow what it says here. It says you feed the integer 4, and you're getting a function. So I can capture that function in a variable, right? So I call it quadruple because that's what it does. It's a function, okay? And once I have this function, what can I do with it? There's only one thing you can do with the function. You can call it. Right, okay, you can pass it to someone else. But here I'm going to call it with 5, and then the answer is 20. Okay, because the quadruple function here multiplies with 4. And then I feed in 5. Now, that was mul_by 4. Now consider mul_by of 10. That's the function. So I call mul_by of 10. That's a function that multiplies its parameter by 10. And why not, right? Now, but there is something that's a little bit weird going on. So mul_by returns this function object here that contains what? Its function has parameters and it has code. Somewhere in the virtual machine, there must be code that says multiply n and x and return the function. And it's clear what the x is that's being multiplied. That's the parameter that comes in here. But what is n? When I called mul_by of 4, n was 4. When I called mul_by of 10, n was 10. But so that n must sometimes be set to 4 and sometimes be set to 10. And how does it know which one to set it to? So really what that means is that mul_by 4 must return something quite different than mul_by 10. Both must return the code, multiply the first with the second. But mul_by 4 must have also retained the memory that n is 4. And mul_by 10 returns a function that retained the memory that n is 10. And that is exactly what happens. So there's two parts to what a function really is. The function is the code, the instructions of what needs to be done. Take this variable, take that variable, multiply the two, and return the answer. And it is a setting of what's called the free variables. The variable x here is bound because it's this parameter. We know what x is. But the n here is not defined within the scope of the function. It comes in from the outside. So for what mulby really returns is it says, I herewith hand you this code that multiplies and n is 4. When you call mulby of 10, it hands you the code that's written here and the fact that n is 10. So you can think of that you get two pieces. You get a bit of code and you get a table of the free variables. Such a thing is called a closure. I don't know why. Why the name is there, I never found a very pretty name. But a closure is the code of the function plus bindings of its free variables. So again, a variable is a free variable if it's not defined in the body of the function. So in this function here, the body is n times x. X is defined as a parameter. N is not defined anywhere here, so it is a free variable. Mulby of 4 returns the binding of n to 4 together with this code. Mulby of 10 returns the binding of n to 10 together with this code. Such a thing is called a closure. And it's perfectly natural. It's simply that these function objects, they remember what the settings of all the variables are. Yes?
What would a call to just mulby by itself return? Would it actually just print out 4 times n, or?
Oh, I see. If you can find out. Well, it's easier to just for me to do it instead of to say what it would be. So here's mulby, right? So and you want to know what happens if I say mulby, like that. It does nothing. Let me do it a little differently. What I've just written is exactly the same thing. I just replaced the def with a val. And now it tells me, when I print it out, when I ask you what's mulby, I can ask it again. It says, oh, it's $lambda $1394 / whatever. So that is a pointer to the object that implements the function. Now let's try to see what happens when I call mulby 4. So we can't look inside, unfortunately. That's again a function, so we're just getting something inscrutable. Let me call mulby 10. I get a different function. You can see it somewhat looks different. And the difference between mulby and 4 and mulby 10 is somewhere inside. This fellow says, I remember that n is 4, and this one says n is 10.
So just an object that points to the object.
Yes, yes. And of course, if I say mulby 4, 5, then you get an actual number.
If you do mulby 4, will it point to the same object?
I don't think so. Yeah?
I accidentally looked at your future slides, and I also know from previous knowledge that this is called currying.
Yes. Yes, it is, and we'll get to that on Wednesday. I don't want to spoil the fun.
Is there any syntactical advantage to using def or val over?
It's just the reason I didn't do this on the slide is that having taught this more than once, I know that a lot of people, when they see an arrow here and an arrow there, their brain freezes up. And so the def thing seems to be less threatening, right? Because
Do you use val? Or?
so over here, you know, there's a def that looks kind of perfectly normal. This part kind of looks perfectly normal, and so you get perfectly. That's the I did it, but they're syntactically completely equivalent.
Okay.
The only reason that you have no choice is with the recursive function. With the recursive function, you must use def because otherwise you don't have the name available. All right, so that's a closure. So a closure captures all of the free variables to whatever the current settings are, and then it has them when it needs them. Next thing is just a bit of syntax, not really hard. Scala is very nice about inferring type parameters when it can. So here I'm defining a function twice. Twice takes a function f that maps integers to integers, and it takes an integer x, and then it computes f of x. It's just there for the example. It doesn't do anything. It's not very, very useful. So now I'm calling twice, and I'm calling it by saying x gets mapped to 42 times x as my function. Notice that here I'm not specifying that x is an int. The compiler is smart enough to figure out that twice expects a function that takes an int, and therefore this x must be an int. That saves me a little bit of typing. I don't have to say x colon int. I'm sure we've used that before because it's such a convenient feature. Just want to point out that the compiler does this. So it also works well with generic types. Here I'm using the library function map. Map is defined as follows. It's a function of the generic type list of A. It takes a function that maps A to B, where B is, again, anything at all, and then it produces a list of B. So over here, I'm saying I want to map x to x times x. The compiler now goes through the following steps. It says list 1 through 3 is a list of ints, because it can see the ints inside. Therefore, A must be int. Therefore, f maps int to something. Therefore, x must be an int. Then it keeps on going and said, if x is an int, x times x is an int. That means b is int, and the output is a list of int. So it has a little theorem prover to figure out these constraints, to solve these constraints, and it does all that type reference. It's, of course, a nice thing to have. Now, a couple more simplifications you can make. Over here, I've used this x, and I've already done that in the last slide. I should have maybe not done that. Notice this x here has no parentheses around it, but when I have 2 or 3 or 4 parameters, then I do need to have parentheses around it. So the rule is that if there's a single parameter, the parentheses are optional. And I should not technically have said that you need parentheses with 2 or more parameters. You need the parentheses also if you have 0 parameters. So only if you have 1 parameter are you allowed to make it. Other functions with 0 parameters?
Not in a pure sense.
Yeah, they don't really, in a pure language that would make no sense, right? Because you could just return the return value always has to be the same, so you could replace them by the return value. In an impure setting, functions with no parameters are common. So if you think of that you want to concurrently schedule a bunch of tasks, then you could think of them as each of them as a function with no parameter. Or the body of a loop that transforms the variables, you could think of it as such a function. So, but we're not really going to run into them in any meaningful way. So now comes the last and most glorious simplification of them all. Sometimes it happens that the variable x only occurs once on the right-hand side. Here's an example when that does not happen. You have 2 occurrences of x. But let's say instead of x times x, it was x times 0.5. Then on the right-hand side, you would only have 1x. In that case, you're allowed to replace the variable that only occurs once with an underscore, and then you don't have to declare it. There's no x error. So this is the function that multiplies its parameter with 0.5. Doesn't get any shorter than this. Yes?
That would be more of a preference, or is it more efficient to use?
No, it's just a shorter.
Okay.
It's just a syntactic shorter. So it does the underlying thing is exactly the same thing. It still has to build the function. Now, the underscore means x here, or whatever, the parameter that no longer has any name. If you have 2 underscores, then they mean x and y. So this is one parameter, and this is a different parameter. So this is the function that you see up here that has 2 parameters, x and y, and that computes whether the first one is greater than the second one. Now notice that you can only do this in lucky cases. You can't do it here because underscore times underscore is not x squared, it's x times y. Each underscore is a separate variable. Also, it turns out that when the variables are inside function or method calls, this transformation does not work for not very clear reasons. But for some reason, they haven't gotten it to work there. And so it only works when they kind of appear at a reasonable top level. I can never figure out when it actually works and when it doesn't work. And if I find myself in a situation where the parameter only occurs once, I will put it boldly go and replace it with an underscore. And if the compiler doesn't complain, great. If not, I just put the variable back in. Seems easier than to find out exactly what the rules are. Also, every once in a blue moon, this thing here fails where I think the compiler should figure out the type, and for some reason it can't. And then I first carefully look and see whether I didn't make a mistake, because oftentimes I did. But once in a while, I just have to go and put in the types. And once you have to put in one type, you have to put in all. And this happened to me this morning, actually. So I had like a list of strings and a string and a string, and somehow it couldn't figure out one of them. But then I had to put all the types in. Yes?
Okay, I wanted to ask, so the underscore is like a special because it will just assume that's the one like variable that's being used?
Yes.
Okay.
Yeah, so the underscore is completely special, right? This is magic syntax. So in Scala, the underscore has about 9 different meanings depending on where it occurs. And so you can get a catalog of them all if you Google for underscore in Scala. But it always means something that's somehow variable, and one should be able to figure it out. For example, one other meaning of an underscore is if you want to import all of everything from java.util, you say java.util.underscore.
It's not
Star.
Not a star. It just means because well, it's consistent. The underscore means something. So I want java.util.something. And here I say, figure out whether something is bigger than something else. Each underscore is something different. So here I'm sorting this array in reverse order, right? My normal comparison is something less than something else. And by having the comparator like this, it flips the sorting and it comes up then as 3, 2, 1. So the last thing I want to talk about is reductions. So map is a very fundamental thing. You have a list of values, and now you want to transform those values. You give a transformation function, all of the values get transformed one by one. In the lab, you're going to see another function called filter that you can use to throw away values that you decide that you don't want. You get a shorter list with some of the values thrown out. But you still have a list of values. And at some point, you might want to have an answer that combines all of the values in some way. And reduce is the general mechanism for doing that. It combines everything that is in the list by a given operator. You may have heard that Google invented a map reduce algorithm years and years ago, and they didn't actually invent it. That map reduce has been existing for ever since Lisp existed, and the functions were actually called map and reduce even then. What they did is they made it so that it parallelizes. So if you have a large data set, then you can distribute the data set in Google's distributed map reduce over a large number of machines. Each of the machine can do whatever mapping, whatever transformations it wants on its portion of the large data set, but eventually they all have to come back together into a single result. And that's the reduction step. They first get reduced locally on each machine so that you have a single answer for each machine. Then those single answers from the whatever 1,000 machines or so get combined to the whole thing again. So that's the more complicated map reduce. We're doing the map reduce very simply just on a list. We have a list of value, and so in a typical transformation you might call map, you might call filter, you might call map again, so that each of the values gets transformed into whatever we want. And then finally, we do need to combine them all. that combination is done with the reduce function. So let me pitch this in a different way. Last time we've written this function called sum. And what did sum do? It summed up all of the elements in the list. And it was 3 lines of code. If you remember, you take the head of the list plus recursively the sum of the table. And what if you want to multiply all of the elements in the list? Well, then it's the same code, right? Except that you change the plus to times. What if you want to have the smallest element in the list? It's the same code, except you change the plus or the times into minimum. So it's always the same kind of thing, and it would be nice not to have to rewrite that recursive function every time that you need it. There's only one small piece of different functionality, and that is the operator that you use to combine 2 elements. That's the job of reduce. It takes a list of values and an arbitrary operator, and then it applies that operator to all list elements. So here, for example, I'm calling reduce with the operator that adds 2 values together. That's going to be the sum of all of the elements. And I can write it much easier on the I can say reduce the list by the plus operator. That just adds them all together. If I want to compute the product, then I would just put a star here and I would get them all multiplied. If I wanted to have the minimum, well, then I do have to pass a function xy such that, and then if x is less than y, then x else y, or call math.min. And then I'd ultimately get the minimum of all of them. That's reduce. It's easy to implement reduce. I've just done it here. So reduce takes a list of integers. I'm only doing with integers here. It takes an op that takes 2 integers and maps them to an integer. I think plus, times, whatever. The result is a single integer. That's the whole idea of reduce. I no longer have a list. I've condensed it down to just a number.
You pass this an empty list, and what happens?
Well, I can't pass an empty list because I wouldn't know what to do with an empty list. So let's say the operator is plus, and then I pass an empty list. What would you want to get back?
Well,
No, you don't get the list back. You get an integer back. That's the job of reduce. It takes a list of numbers and it gives you a single number. It can't give you nothing. Nothing is not a number.
isn't it possible to pass an empty list in here?
See what happens.
Just that tail list.
So you want to reduce nil and plus. Okay. And is it possible? Of course it's possible. Well, maybe it doesn't like nil. I'll give it a... Well, it doesn't say it doesn't.
Click on
Flip? I don't want to flip. Let me give it a list of int that has nothing in it. See if that likes that better.
So it's just
Well, that's why these stupid worksheets, you can never tell. So it says, so the illuminating error message is, it wants a list of int, and it's getting a list of int. And it expects a util list of int. Oh! Because I imported java.util.whatever, and there's a java.util.list. Okay, so let's take that out. In that case here, and I'm sure now it'll work with a nil.
unsupported operation.
And now what I get is, it can't take the tail of an empty list, so it doesn't work. So I can call it, but it throws an exception. And that's just the contract of reduce. You need to give it a list with at least one element. It can't figure out what the default would be. I mean, a sensible default for adding might be 0. a sensible default for multiplying might be 1. For min, it might be what integer max value. And so reduce doesn't handle that. There's a cousin of reduce that does that we will see next Monday.
Is it like reduce or default?
Well, that's the one that you're going to have in the homework. And okay, then I won't give away what it's called in Scala. It has another name. All right. So reduce expects to have at least one value, otherwise it will not work. So that's a very good call. And so we're saying if the list has length 1, so that's what I'm saying here. If the tail is empty, that means it has length 1. Then I'm returning the head of the list. So if you ask me to reduce the list only containing 5, the answer is 5. I didn't even apply the operator because I can't. The operator always needs 2 values. Otherwise, I return the combination of the head and the reduction of the tail. So I might, if op is summing, I would add the head to what ultimately will be the sum of the rest. If it's a product, I will multiply the head with what later will be the product of all of the others. And so that way I extend the operation one step further. So that's what reduce does. And what's great about reduce is that the same thing can do whatever reduction you want. You just pass in a different operator. In the lab, you're going to see that it doesn't have to be plus or minus. There's a more creative use of an operator that does something that you'll find eminently useful. So this lab here has 2 parts, and I want to make really sure that everyone gets to the second part. So what we're going to do is you're going to do step 1, 2, and 3, and then we'll have a short conference. And then afterwards, everyone is going to, even if you didn't get step 3 done, you're going to skip ahead to step 4, and we're going to mess with reduce for 15 minutes. Because reduce is so important, I want to make sure that everyone does that. All right, so go ahead with steps 1, 2, and 3, and in 20 minutes or so, I will say a few words about those.
I'm so tired.
I didn't know we were married. I thought we were like married. Yeah. Because like
So is even is going
yeah, I'm
to
curious.
take
Yeah, I did it that way. And then I rewrote it so that I didn't use that because I realized with a very long string, you'd have to use it like
Because you have 32, the return value should
Well, it happens under.
yeah, we're 32.
So what's not, you don't never, when you're off,
Right, and you want to use basically.
I was browsing the internet the other day and I saw that